Okay, so stoichiometry, here we go. Remember that when we're talking about the masses of all the elements, the standard is carbon 12. Everything else is relative to carbon, okay? They decided that a mass would be defined as exactly 12 atomic mass units of carbon, and then they did everything relative to that, okay? Mass spectrometer is a device used to measure the mass of atoms or molecules. That's what you're going to watch a video on. It's going to kind of explain a little bit more how it works. Here's an overview. Are my pictures not showing up? Okay, okay. Sorry, there's supposed to be a picture there. You have it. I've been having trouble with my pictures not showing up on my PowerPoints today. I don't know why. So if it does that again, I may have to stop and reload. Okay. So mass spectrometer is an instrument, and it uses to determine the masses. It does that by deflecting their ions into a magnetic field, and then the ions are separated by mass, and then that data is graphed. Okay. The average atomic mass, of course, is the average masses of all the isotopes that are present. Percent abundance is how much of that percentage is a certain isotope. And, of course, percent abundance is part over whole, the number of atoms of a given isotope divided by the total number of atoms of the isotopes times 100. So it's basically part over whole, right? Okay. To find the average atomic mass, we do that weighted average thing. So in this case, this is neon. This is just two different representations of the mass spectrometer of neon. The first one just gives you relative intensity, but the second one is actually going to give you relative numbers. And so since it's based on 100, you could say that 91% of the neon atoms would have a mass number of 20. Looks like 3% would have 21, and then 9%. And then you can use those numbers to actually calculate the average atomic mass, which guess what we're fixing to do? That. Okay.
With the numbers?
Okay, my pictures are not showing up, so let me pause. Okay, pictures are back. So in this particular case, we have a sample of copper vaporized, and it's injected into the mass spectrometer, and then here's the results. So we're going to use this data to calculate the average mass of the natural occurring copper. Gives us our mass values in the problem. For copper 63, we're going to use 62.93. For copper 65, we're going to use 64.93. And then it's giving us the relative number of atoms. So we're assuming that this is 100, so this could be 69%, right? And 30.90%. So because we have a percentage to get the average atomic mass, we would take 0.6909, because that's a percentage, and we're going to do it weighted average, times 62.93 plus 0.3091 times the 64.93. And then that would give us a total of 63.55 AMU. Now, why did I move the decimal on those two? Because they're percentages. Okay, just want to make sure. Sometimes the simple, easy stuff we forget about because we're expecting it to be hard. Okay. Any questions on what I did there? Incidentally, that's the way your grade is calculated in here too. It's a weighted average. Take your percentage of each score and add them together. Test being weighted the most. Okay. We good on that? And we just read the peaks like that. There's mass spec. That means that this particular isotope came out with that mass, and the second one, and it just gives you percentages. Okay, the mole. We know what the mole is, right? Okay, Avogadro's number, 6.02 times 10 to the 23rd. It's the number of particles in anything. When you have a mole of atoms, a mole of molecules, a mole of ions, you can have a mole of formula units. And, of course, it's the number of carbon atoms in exactly 12 grams of carbon-12, and it's a counting number. Okay, so here's exercise 2, determining the mass of a sample of atoms. We have Americium, which is a man-made element. It does not occur naturally, and it can be made in very small amounts in a particle accelerator. So it says, and when we mean very small amounts, it says calculate the mass in grams of a sample of Americium containing 6 atoms. Don't know even how they counted that. Okay, so 6 atoms would be 6 atoms. And what am I going to do to get rid of atoms? 6.02 times 10 to the 23rd, because there's that many atoms in a mole, right? Okay, so I can cross out atoms, and then I can use the molar mass of Americium. Periodic table's on the wall. It's 243. So we would do 243 grams of Americium over 1 mole.
Does Americium only occur in one stable isotope?
So what happens is it doesn't exist for very long because it's man-made and it's there and it's gone. So they don't really know, honestly.
Okay.
I mean, I imagine that it has more isotopes, but if you look at the periodic table on the wall, the things that are in parentheses, they don't know enough about it. So that's why it's whole numbers.
Okay.
Yeah. Okay. And so when I do my magic calculator, I should get 2.4 times 10 to the negative 21 grams of Americium. If I was following sig figs, it would just be 2, because 6 atoms is 2. Has only 1. Okay? Makes sense? We good? Is this ringing a bell? A rusty bell, but it's ringing nonetheless. Okay. In the next problem, determining moles and atoms, it's actually asking us to calculate both the number of moles of atoms and also the total number of atoms in 10 grams of aluminum. So because it's asking it in 2 parts, instead of doing it all in one step like we just did, we're going to do it in 2 separate steps because it's asking us specifically how many moles. So we're starting with 10 grams of aluminum. And the molar mass of aluminum is 26.98. So that's going to come out to 0.371 moles. So there's our first answer. Actually, I mean to not do boxes in here. I actually tell y'all not to box your answer on the AP exam. Because if you accidentally did something wrong and you boxed it, but you did something right, sometimes they might give you a point. But once you box the answer, that's all they, yeah. So don't box your answers. I will probably still do it on accident because I'm so used to it, but try not to. So then we're going to take that 0.371 moles, and we are going to multiply 6.02 times 10 to the 23rd atoms over mole. And then we get 2.23 times 10 to the 23rd atoms. Okay. Oftentimes on the AP exam, they actually don't ever, not ever, but they usually don't have you do one big problem. They usually will do it in steps. So like they might tell you, calculate how many moles. And then in the next step, they'll say, calculate this, and you use the moles from the previous step in the next step. And so when you're working an AP problem and they give you the grams of something, if you don't know how to do anything else, convert it to moles. That might be a point. I mean, honestly. Okay. Exercise 4, you're going to work on your own. The answers are attached. I usually will give you more problems in the notes than I will work because there's no reason to beat a dead horse. We can do conversions. If you need more practice, the answers are attached, so you can do that on your own. Okay? All right, that brings us to molar mass. Okay? So we've been using the average atomic mass of those elements. Now for molar mass, we're just going to take those average atomic masses, and then however many atoms are in the formula, we add them together. Okay, a couple of things. We're going to be talking about empirical formula in a minute. And then for, if it's an ionic compound, the empirical formula is just its normal ratio. But if it's a covalent compound, you can have empirical molecular formula, which we'll do in a moment. Formula weight is the same as molecular weight, which is the same as molar mass. Okay, years ago we called ionic compounds, we said it had a formula weight. And covalent compounds, we said it had a molecular weight. And that got confusing to chemistry students. So they just came up with molar mass, which covers both of them. And it's the mass of 1 mole of a compound of some sort. Okay? But sometimes there's old school things, and you might see formula weight or molecular weight. They mean the same thing. One's for an ionic compound, one's for a molecular compound. Yes?
You said empirical formulas are only for covalent compounds?
No, I did not say that. Molecular formulas are.
Oh, okay.
Empirical formulas, the definition of an empirical formula is the simplest ratio of a compound. Okay? So for an ionic compound, that's all there is an empirical formula, because in ionic compounds, remember, there's only one way for those to go together based on their charges. Mm-hmm. For a molecular compound, the empirical formula is the simplest ratio, but the molecular formula is what it actually is. And we'll talk about that in a minute, because guess what we're going to calculate today? Empirical and molecular formulas. Yeah. Okay? All right, so moving on, we're going to calculate the molar mass of this compound called juglone that's obtained from black walnut trees. Okay, so I want y'all to do this together with me. We have C10H6O3, just to remind you how to calculate a molar mass. The nice thing is a lot of times they might give you a molar mass in a problem because they're trying to speed you along, but I'm going to make you calculate them throughout the year. So carbon, we have 10 times 12.01 plus we have 6 times 1.01 plus oxygen is 16, right? No, 3 times 16. Sorry about that. So we do that, and we should get a 100 and something, 170 something, 174.1 grams per mole. Okay. So in the next problem, it's asking you to see how many moles that is. That's an on your own. You can use the molar mass to do it on your own, and I give you the answer, so you can see that. Okay. Because mole to gram, gram to mole conversions, you should know how to do that from Chem 1. I refreshed your memory, but yeah. And if you can't remember that stuff, you need to go like do some reconnaissance missions on videos online, like Crash Course. Bozeman videos are great. Sometimes I will assign you Bozeman videos to watch, but you can always go look at them if you want to get. Did y'all use Bozeman at all for physics? Okay. You do for biology. So if you go to the Canvas page from AP Chem, down at the bottom there's a tab that says AP Review Videos, and you click that, and there's actually several links like Khan Academy. I don't know if Crash Course is in there, but the Bozeman videos are on there. But let me just say the Bozeman videos are divided up a little bit differently because until this year, the AP Chem was based on 6 big ideas, which I did not teach by big idea. I taught in a way that made more sense to me. So sometimes you might have to dig around for like big. So like we're on stoichiometry, so it seems like it should be in the beginning, but it was part of big idea 3, and so you got to go down there and find. So you can find those to watch as well. And then there's just good old-fashioned YouTube, how to calculate a molar mass.
What is the number in the box?
Yeah, on the part B.
Oh, it's a -2. When I converted from PDF, I did not realize that this did this. When I converted from the PDF to the Word document, it goofed up some stuff. But if you're getting that out of black walnut husk, you should imagine it's a small number, right? So it's a -2. Yeah. And if you calculated it with a +2 and you didn't get the answer they got, then it was a -2. Deductive reasoning, right? Okay. I think that brings us to percent composition. Exercise 6 and 7 are also a work on your own. So that's going to take us to elements that exist as diatomics. Diatomic molecules, we know what those are. Brinkelhoff. Yeah, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. There are other ways to remember the diatomics. Different teachers use different ones, but we know and love Brinkelhoff. Okay. Also, you can add hydrogen and then start with nitrogen and go over to fluorine, and it makes a 7. But you got to remember to include hydrogen. It's also the gens and the halogens. Halogens, hydrogen, nitrogen, oxygen. But you got to remember that you have to say the halogens in that. Because chlorine, fluorine, and bromine do not end in gen, but they are halogen. That's why I don't like that way, because people will be like, oh, fluorine doesn't end in gen. It's the halogens. So there's your 3 ways right there. Okay, others that you need to be aware of that you do not have to memorize are phosphorus and sulfur, and then of course carbon can do crazy things and it's going to share. So it's very rarely ever by itself, but who can remember how many bonds that carbon needs? 4, yay! Okay, percent composition, again, part over whole times 100. In this case, the whole is going to be the molar mass of the compound. Okay, so we're going to do one quick one of, consider ethanol, C2H5OH. So let's do this together. What is the molar mass of MM? Molar mass is 46.08. So for carbon, we would say 2 times 12.01 divided by 46.08 times 100 gives us 52.14%. hydrogen, 6.06, because there's 6 hydrogen in that formula, right? I did 6 times 1.01 in my head. Smart like that. Times 100 gives me 13.15%. And then we only have 1 oxygen. 1 lonely oxygen, which is 34.72%. I can double check myself to see if it adds up to 100%. Okay? Now, here's the thing. You will very rarely have to actually calculate a percent composition straight up. Usually you have to know how to do that to be able to do empirical and molecular formula. Okay? Any questions on what I did there? Yes.
With the percentages, do you always want to score into 2 decimal places like that?
Whatever. You can do 1.
Okay.
Yeah. It's just habit. Yeah. There's really no, like most time I say 2%, but you'd get, I mean, if you rounded all that and got that, you'd still be cool. Yeah. Okay. Any other questions? Okay, exercise 8 and 9, work on your own. The answers are there, which brings us to empirical and molecular formula. Okay, so if you remember when we're talking about empirical molecular formula, empirical is the simplest ratio. Okay, so and then molecular is what it actually is. Because if I were to take these compounds, like if I were to take C2, hold on, I didn't write very well, C2H2, which is ethine, that's a compound, ethine, and I were to take C6H6, which is benzene. Okay, 2 different compounds, 2 totally different properties. Ethine's a gas, benzene is a liquid, it happens to be a carcinogen as well. But if I were to do a percent composition on those, they would come up with the same ratio of carbon to hydrogen, right? Okay, and then I would try to figure out their formula. So their empirical formula would be CH. Okay, so if I were to do an empirical formula and do all the math, I would get their empirical formula would be CH. Okay, that's the simplest ratio. Sometimes their empirical and their molecular formulas are the same. For instance, if I had C3H8, can I simplify that? No. So its empirical formula would be its also molecular formula. But in this case, the C6 and the C6H6, I can simplify that to be an empirical formula of CH. Okay? So how do I calculate this? Okay. So this is just giving you an example. I kind of show you a slightly different way. And there's more than one way to work this. Like today in class when they did the example problem, the last one we're going to do today, some of the kids worked it completely different. Or they kind of worked at it backwards, and they still got the right answer. So you can do that as well. Okay, as long as it's sound chemistry, they'll take it. But if we have CH2O, which is the empirical formula for any carbohydrate, then we could have different variables of that. For instance, that's the empirical formula for glucose, because glucose is C6H12O6. And so we could figure out, remember when I would have y'all do empirical formulas, I would have y'all do this, CH2O, and then I would put that little N there. Do you remember that? Not everybody does that, but I just found it to be easier. And then we would go and say, to solve for N, we would do the molar mass, which you must be given, right, over the empirical mass. And then how do we calculate empirical mass? It's the mass of the empirical formula. Okay? Does that ring a bell? Okay. So let's work a problem. Okay? So we're going to do the example. Hydrates, I think we talked about this. If you have a hydrate present, you have to calculate water just like you would for one of the elements. And then anhydrous means without water. I boiled off the water, drove it off. All right, so I have a compound composed of carbon, nitrogen, and hydrogen. When I have 0.1156 grams of this compound, when I react it with oxygen, in other words, I combust it, I get some carbon dioxide and I get some water that are collected. And it wants me to determine the empirical formula. You didn't do this in pre-AP Chem. I gave you percentages, or I gave you straight up like it had this much percentage of carbon or whatever. I didn't give it to you as CO2 and water. This is what's known as combustion analysis, and you have to know how to do it. Okay? And so it's fairly straightforward. You just got to keep up with everything that you need to keep up with. So the only thing that I can use at this point is my carbon dioxide and my water, because that's what it burned, and so that's what I know it has. So I'm going to start with the CO2, and I know that I had 0.1638 grams of CO2. And what did I tell you? With the if in doubt, if you don't know to do anything else, what should you convert to?
Moles.
Moles. So we're going to convert to moles of CO2, and then we're going to go from there. Okay? So I'm going to divide by the molar mass of CO2, which is 44.01 grams per mole of CO2. So I'm in moles of CO2. Remember that mole ratio? Here's what I'm going to do here, and I'm going to say, for every 1 mole of CO2, there is 1 mole of carbon. And how did I know that?
The empirical formula.
From the formula for CO2. Okay? So I'm going to, because I know what I have to do the last step, I'm going to convert that to moles, and I'm going to write that down, 0.00372 moles of carbon. I'm going to do the same thing for water now. Let's do water in red. 0.1676 grams of water. Does anybody remember the molar mass of water?
18.02.
Yeah, that's ingrained into your head. And I never even made you memorize it. For every 1 mole of water, how many moles of hydrogen are there? 2. Okay, and then that's going to be 0.0186 moles of hydrogen. Now, normally we would be, oh, let's divide by the smallest or whatever, but we still have some nitrogen that we need to account for. Okay, so the way we're going to do that is we're going to convert our carbon and our hydrogen to grams. Because if I have the grams of hydrogen and the grams of carbon, could I get the grams of nitrogen?
Yes.
How?
Subtract from the
total sample, right? So times 12.01, and then that's going to be 0.0447 grams of carbon. I'm going to multiply for hydrogen. What am I going to use? Huh?
1.02.
What did you say, Thomas Kidd? Thomas Kidd is correct because this is not diatomic when it's in a compound, right? Good job, Thomas. And that becomes 0.0188 grams of hydrogen. So now I can go down here. Nitrogen feels like it should be purple. 0.1156 minus 0.0447 minus 0.0188 is going to equal 0.0521 grams of nitrogen. So now to get empirical formula, what do I need to do with my grams of nitrogen? Convert it to moles, right? So that gives me 0.00372 moles of nitrogen. So now to get my ratio, or my empirical formula, I'm going to divide all of the moles by the smallest number of moles, right? So divided by 0.00372 is going to be 1. Divided by 0.00372 ends up being 5. Divided by 0.00372 ends up being 1. So my formula is CH5N, and that is my empirical formula. Okay? Any questions? Fun, huh?
Wait, okay. So
I try to do different colors for the steps if y'all didn't get that.
After you converted the nitrogen to moles, why would you divide the other amounts of moles from carbon and hydrogen?
Oh, because the steps in molecular form to get empirical formula is you convert everything to moles, and then you divide by the smallest number of moles that you have, and that gives you your ratio of atoms to atoms in the formula.
Okay.
Now, if you recall, if it doesn't come up to a whole number, you have to multiply by an integer to get it to go to a whole number, and you have to do that to everything. Do you remember that?
Semi-ish?
Yeah.
Okay.
This was in the packet.
It is in the packet. There's a big combustion analysis one's in the packet. That's kind of tough. I would suggest you try it. Yeah, I remember that one. It's a tough one.
Okay, so you have to multiply everything by an integer.
Only if it comes up to a decimal. It's not here, so you don't have to here.
Oh, okay.
Yeah, we're just figuring out the ratio.
Okay.
Okay.
So that's the empirical formula for this combustion analysis.
For this particular compound, that is the empirical formula. Now, if we wanted to know the molecular formula, we would have to know its molar mass, and then we would do the whole molar mass divided by empirical mass.
Okay.
Okay? All right. Fun, huh? Oh, this is the easy stuff, guys. I'm sorry. If you don't know what I did there, there's the steps. They're right there listed for you, okay? Cameron and Elise, we did not do this in regular chem, so y'all are probably a little bit lost. So I would highly suggest to go watch one of the videos on it, because we didn't do this at all. That was not something we did in there. So after we do this unit and the gases unit, then we're going to get to things that none of them have done before, so then you're going to be on a level playing field. But the first this first unit, you're a little bit, but it's okay. It's all, yeah. None of that was hard. It's easy to do. You just got to practice it, yeah. Okay, so you know what I like to do when I want y'all to work on a problem. What am I going to do? Freeze it. Pause the video. All right, and here you go. Okay, so there is more than one way that you could have worked this. What Thomas just showed me is a different way. A couple of people in the previous class worked it as well. So what some people did here, tell me if any of you did this, because there was a molar mass already given to you, they took the percentages and multiplied the molar mass by that, and that gave them the molecular formula. Because those are the percentages, and there's the atomic mass, or the molar mass, so they would multiply 71.65 times the molar mass, got that number, etc., etc., and then they got the molecular formula, and then you divide by and simplify it to get the empirical. So you can do it that way as well.
That seems way faster.
Okay, that is faster in that respect, but if they didn't give you a molar mass, you still have to know how to do empirical formula. So you would still have to know how to do, this makes a circle, this little part here. What? You'd have to know how to do it that way, okay? If they didn't give you a molar mass. If they just said, here's the percentages, calculate the empirical formula, then the way that Thomas did it wouldn't work, okay? So you'd still have to know about this way. Yes?
The empirical formula, do you have to do like the parentheses and end?
No, you do not. You can, if it said, and quite frankly, if they were having you do this would be a multi-step process. They would say, probably have you convert things to moles, and then probably say, what's the empirical formula? And then they would probably say, what's the molecular formula? So if they say, what is the empirical formula? You would just answer that. If you did the thing in the end, they probably wouldn't do anything about that. That's a way that some teachers have chosen to teach it so that they could easily say, there's how you get that in. Instead of that long explanation of do this and get the ratio, just molar mass over empirical mass. Okay, I'm going to stop the video, but I will leave this part up for you.